To round out our discussion of Dijkstra's algorithm, we need to do a complexity analysis. So the question is, how do we actually implement this stuff? Right? In order to understand the complexity, we need to be able to think about how this algorithm would actually go into code. And to do that, we have to think about what we need to keep track of. Okay, so think about the progression of the algorithm as keeping track of a list of all the nodes and their shortest known distance to A. Okay, so to do this, what we'll do is we'll implement a priority queue. So we'll use a priority queue, and I'm just going to abbreviate this PQ. So we'll use a priority queue, or a PQ, to track essentially the shortest known distance from each node to A. The shortest distance from each node to A. All right, so if you haven't run into a priority queue before, this is what a priority queue does. It's not just a queue, right? A priority queue is something a little bit more subtle. So a priority queue is it's a data structure that stores orderable elements. So for example, numbers, right? So here's your quick primer on the basic data structure priority queue. So it stores, let's just say numbers, or generally orderable things, right? Stuff where we can ask the question, what's the biggest, right? Or what's the smallest? And it has the following. So imagine a priority queue having the following elements. So it has a vertex, and then the distance, the best known distance for that vertex, and then it has a vertex, and the best known distance for that vertex, it has a vertex, and the best known distance for that vertex, and so on, right? And then all the way down to the end, I'll just go all the way to Vn, Vn, dVn. There it is. Okay, so that's how we'll use the priority queue. The priority queue is going to have a vertex, and then associated with that vertex, it'll record the best known distance from that vertex to A. So this is best known distance, the shortest known distance from V1 to A. Right? This could be infinity, right? It could be that we don't know of a path yet from V to A, right? But that's what dV stands for. And we have essentially three operations that we're allowed to do on a priority queue. So 3 operations. Okay, and here's the names that I'll give these operations. So the first one is insert. Okay, so this is on priority queue named queue. Okay, so insert, I can say let's go to the priority queue queue, and let's insert a vertex and a weight. Okay, so what does this do? This adds vertex v to the priority queue, and then assigns it the number or the distance dv. Right. So what does this do? Adds v to q with distance dv. Okay. So the next thing we can do is we can say, let's update. Update. So what does update do? Well, it goes to the queue, it goes to a vertex. That vertex has to already be in the queue, and it gives a new distance. So what does update do? It changes the dv of v in queue to dv prime, right? So it goes to that node, the node that is specified here in the queue, and it changes its distance. And then the last thing we can do is delete min. Okay, so what delete min does is it goes to the queue, and we say, and it just takes the queue as an argument, and it says, get me the thing with the smallest dv. Okay, so this removes the vertex, the v, with the smallest dv value and returns it. All right. Okay, so let's think about how much time each of these operations take. So if we think of the priority queue as initial, and we'll go through the details of this in a minute, but if you think of the priority queue as having all of the nodes in it, all the nodes in the graph, let's see if we can come up with a way of writing down the time complexity of each of these operations. Now, I'm mostly going to focus on these two, on the update and the delete min, right? Because those are the ones that we're going to be doing a lot throughout the course of the algorithm. Update we'll do anytime we add a node to our tree. Then what we'll do is we'll go update all of that node's neighbors' potentially minimum weights. And then delete min, we'll use that to decide which node to add to the tree. Okay, so these two things will be used repeatedly throughout our algorithm. And we'll do those details in a minute. But let's think a little bit about the time complexity of these. And it turns out the time complexity of these depends on how we've implemented our priority queue. So there's essentially two options that we'll concern ourselves with in this lecture anyway. There's two options for a priority queue. For PQ. We can either implement as a heap, a min heap, and perhaps I'll go over how a min heap works in the synchronous session. If you want to know sooner, go look it up. It's a valuable thing to understand. So we can either implement it as a min heap or as an unordered array. Okay, those are essentially our two options that are relevant to this problem. Min heap or an unordered array. A minimum heap is a certain kind of binary tree representation of a bunch of data. And it's a very fast one. It's one where some of these operations are blindingly fast. An unordered array is just what it sounds like. We just take the vertices, put them in an array. And in an unordered array, if we want to remove something, we have to go search for, like if we want to run the delete min operation, we have to go through the entire array and find the smallest thing. Okay, so let's start by thinking about the time complexity of delete min. Okay, so delete min, we need a little more space here. So the operation delete min takes order length of the array if it's an unordered array, and so we can call that order v. Okay, so if there's v elements in the array, we'll have to look at all of them to figure out how to pull one out, to figure out which one kind of has the smallest distance, which one is the minimum. If it's a heap, it turns out that it's much faster. It's log v. Okay, and here we're thinking about both of these as being a priority queue containing v elements. Okay, so that's delete min. The update operation then is it takes some time for the min heap, and the reason for that is that when you change the weight on something, that might make that thing the smallest element in the priority queue, and if that's what it does, then that has to be promoted to the root of the heap. We'll go over those details in class, but that's what's going on there. Is it takes some effort, takes some time to reorganize the heap if you change the value here. But in an unordered array, it takes no time, right? You find the element, right? You have the array indexed already by the element. You find it and you change its value, but you don't have to reorganize the data structure in order to record this. So this is a big theta of 1, right? The unordered array updates in constant time. Okay, so we'll use these now. We'll use these time complexities for each of the priority queue operations to think about how to analyze the algorithm overall. Now to do that, we need some pseudocode, right? So let's work through some pseudocode here for Dijkstra's algorithm and actually see where these things happen and think about how often they would have to happen. All right, now I've written pseudocode. I'll walk through the pseudocode, and then once I've walked through it, we'll think about how much each of these loops takes as a function of how we've implemented our priority queue, and actually also as a function of how we've represented our graph. So there's actually two implementation details that we need to think about in terms of how they interact with each other here. All right, so let's go from the beginning here. So I will actually, as I go, I'm gonna I'm going to syntax color my comments. So Dijkstra takes in a graph, and it takes in the identity of a source node. So G is our graph, S is our source node. The first thing that we're going to do is we'll initialize our priority queue. Right, so initialize an empty priority queue. We'll call that Q. Then for each node in G, we'll add that node to the priority queue with 2 pieces of information. We'll record 2 pieces of information for that node. So the first piece of information is its distance, right? And we're going to think of this as the best known distance from node V to S. So if I ever write down dV, what that's saying is this is the best distance that the algorithm knows about so far to the source node. Okay, and likewise, likewise we're going to use this PV to be the next node in the best known path. Okay, so what that means is if I write down PV, then that tells me where to go from node V to get to the source node with the smallest total cost. Okay, and so that's going to be kind of how we're going to store our paths as we go forward here, because there could be multiple ways for a node to connect to some other node, and so PV is going to keep track of that. All right, so once we've got those pieces of information, we stick them in the priority queue, right? So all this is doing is it's saying put every node in the priority queue. Okay, so then we go find the source node, and we initialize its distance to 0. Okay, so what do we know about the source node? It is 0 units away from itself, right? The cost of going from the source node to the source node is 0. And then we say, there's no interesting path from here to the source node because we are the source node. So then we're going to initialize our tree. So VT is the set of nodes in the tree, right? That we're going to build up over time. And so at the end, what we hope to do is return this tree. Right? This tree is our set of nodes. And so what we do here is we say we know that we need to add every node to the tree. Right? So what are we going to do? We're going to set up this for loop that ticks exactly the number of nodes times. And each time the for loop ticks, and that's this for loop. Each time this for loop ticks, we're going to add a node to the tree. Which node are we going to add to the tree? We're going to add the node that has the smallest known distance to the source. Okay. So the first time this ticks, what node are we going to add? Well, every single node has a distance of infinity, with the sole exception of this one. Right? So there's only one node that has a finite distance, and it is the source node. So the first node that gets added to the tree in this for loop is the source node. Okay. So then what happens after the source node is added to the tree? Well, let's go down here. So what we're going to do is we're going to call the node that got added to the tree. We're going to call that U star. So U star is the identity of the node that has been added to the tree. Right? So here's where we add it to the tree. The new tree is the old tree, union with the set containing the singleton set containing only U star. And then what do? Well, we search through the neighbors of the node we added. Right? So we add a node to the tree, and then we go look at all of that node's neighbors. Specifically, right, we can look at the neighbors that haven't already been added to the tree. So the tree is considered fixed, but now what we're going to do is when we add a new node to the tree, let's go look at all the neighbors of that node that aren't already in the tree. So that's what this line is doing, is it's going and considering all the neighbors of this node that aren't already in the tree. And then we just update their weights. So all of this is saying after we've added something to the tree, having added it tells us something about the distance from that node's neighbors to the source. Okay, and that's what this if statement is doing right here. So here, what are we doing? We're updating best known distances. Best known distances from U star's neighbors to the source. So to S. Okay, and that's it. That's Dijkstra's algorithm. All right. Then we go back and we add another node to the tree, given these new best known distances that we have. And so it's worth your time to either look this up in the book. The code is very similar. There might be a typo in the book, but this one I believe is correct. Either pause this and look it up, or go to the notebook, look it up in the class notebook, or go to the book and understand how this logic inside the if statement is working. But basically what it's doing is it's saying if this update, like if there's a shorter path through U star for each of these neighbors of U star, if there's a new shorter path through U star to the source, then make that the new shortest known distance. Otherwise, leave it the same. Right? And if you change the shortest known distance, update it in the priority queue. So now the question is, how do implementation details affect how fast this algorithm operates?